not doing. The fan on my computer is blowing, so I thought I was recording. So now I'm starting late again. I'll make my note. I always make the notes available though, so hopefully it's not that horrible a deal. Okay, so put another way, this can't be greater than 0. So what we have is we have the only possibility now. We know, right? We know that for an irreversible process, this integral can't be 0 because it's only 0 for a reversible process. We know it can't be positive now. So the only thing left is we can write this Q prime, which is T of the reservoir, closed loop, dq over TB, must be less than or equal to 0. And this is for all processes now, right? This is called the Clausius inequality. This is actually a statement of the second law. It doesn't mention entropy at all, right? Because we haven't defined what entropy is, right? We can break up this into two possibilities. dq over t b is less than or equal to 0 for any process. dq over tb equals 0 for reversible processes. All right. Today may be one of those days where your head either expands or it explodes. Because it's hard to know, it's hard to understand how this all makes sense. The good news is after we get through these derivations and discussions of the second law, we're actually going to do some things. Because I know right now it feels like we're not doing anything. In Devo, this is now section 4.4.3. This is the shorter derivation of entropy. And I think this is very elegant. I kind of like it. All right, so first let's start off with some logic. If a reversible process is reversed, almost by definition, only the sign of the value of dq changes, not the magnitude, right? That's the whole point of reversibility, is that the change is so small that we could go the opposite direction just the same. So only the sign changes. So let's write this down. If a reversible process is reversed, dq rev, the amount of reversible heat, changes sign, but not magnitude. If it did, it wouldn't be reversible, right? We could actually use a statement like this to define reversible versus irreversible changes. If you reverse the process and both the sign and the magnitude change, then it's irreversible, right? All right, so what does that mean? That means this. Let's put this into mathematical terms. dq rev over t equals minus 2 to 1 dq rev over t, right? We also know from the Clausius inequality that for a closed process where we return to our original state, dq rev over t equals 0. Right? Now, what we've done, right, we've said for a reversible process, dq rev over t is 0 for a closed process, cyclic process rather. We put a bound on it. We know that for a real process, this must be less than 0 for the system, must be less than 0. But can this be less than 0 for a reversible process, right? So let's go back and do that. Here's what we're going to do. And what I'm going to do here is I'm going to label this not CC, CW, right? In other words, what we're going to do here is we're going to do our closed loop in a clockwise fashion, A returning to A. So think about our process going around in a circle in a clockwise direction, right? And I'm just going to define this clockwise because this is really any process, I'm just defining the direction as clockwise. The reason I want to do this is because it turns out this is not possible. The reason is, come on, if it were possible, then what we would have is we would have the opposite direction, counterclockwise, right? Which is this. Maybe you see what I'm getting at here. Would be greater than 0, right? Because we're just reversing the limits, right? We know one of the fundamental things is if you reverse the limits or the direction, it just inverts the sign. So if a cyclic process, dq rev over t, reversible, if that would ever be less than 0, then going in the other direction must be greater than 0, but this is impossible. We already know that greater than 0 is not a possibility for this. All right, so thus dq rev over t can only be 0. Well, what does this mean? This means that this is an exact differential. And this really means it's a state function. I'm not quite ready to define that because I want to prove this another way, okay? And so now instead of taking a just general loop, let me do a more defined loop. Let me go here from A to B, right? Let me define a few paths. Here's path 1. Right? Let me now define path 2. And let me also define now the exact opposite of path 2, path 3. In other words, path 1 is any path. Path 3 is the exact opposite of path 2. Okay? It's just the exact reverse of path 2. Okay. Well, we know what time is it? Okay, good. We know Now, I'm going to do a cyclic process, right? But I'm going to make it be 1 plus 3. So let me be my return to A, going from A to B through path 1, and then back from B to A through path 3. Okay, so this is the way I'm going to label this. We know that this is 0 for a reverse cyclic process. So I need to be careful here, right? Because these are going to be reversible paths, right? Reversible paths. Then we can say this, okay? But we also know that the path, right, not a cyclic process, but the path of 3 dq rev over t, this should have a rev here, equals minus dq rev over t for path 2, right? Because all we're doing is changing direction. Okay, so what this means, if we label this kind of a different way, going A to B, dq rev t is the same for paths 1 or 2, right? In other words, if I go from A to B via 1 or 2, well, I know 1 and 3 returns us back to our original state, so that has to be 0. I know that 2 and 3 are equal and opposite to each other, so that has to be 0. So what this tells me by implication is that this is independent of path. Which of course is the way we describe a state function. This is exactly what it means though, when we say that it's independent of path. We can think about this in a lot of different ways, right? A real simple way is say that altitude, absolute altitude is a state function. And if we go, the example I always use a bazillion times in my life is traveling from Stockton, pretty much sea level, to Lake Tahoe, which is like, I don't know, 4,000 feet, right? So altitude is a state function, and it doesn't matter that if you drive there, walk there, or fly a helicopter there, 3 different paths, the altitude is the same, and it's based upon the start and finish, right? Now, what we've done here is shown this a little bit more mathematically, but it's not horribly mathematically, right? So once again, we can say that dq over t is an exact differential. Well, we're going to do something that we do many times in thermodynamics. Actually, we do it twice mainly, but this is maybe the first time, is we're going to call dq rev over t something new. We call it entropy. ds is defined as dq rev over t, right? And entropy is a state function. So what we end up with is the more common statement of the second law. Let's go up and look at the Clausius inequality, right? The Clausius inequality is this boxed equation up here, right? Let's change this to entropy language, right? Entropy language would say T ds is less than or equal to 0 for the system for a real process. What does real mean? Real means spontaneous. So the statement of the second law that we usually see is that ds must be less than or equal to 0, right? For a process. The only difference here is there's a t here, but because t is always positive, t actually has no bearing on this, right? If we use thermodynamic temperature where t is always positive, it doesn't really matter whether the t is there or not, right? It's the part inside the integral. So this is really the second law statement that we're used to. But we've kind of, if you think about it, we've kind of come around to it in kind of a weird way. It is kind of a weird way, right? At least it's new. So this is the statement of the second law. And we've, what I mean by a weird way is we've gone to great pains to define an idealized reversible process, and then this gives us a bound. And of course, every process that we can do in real life is a real process, which is irreversible or spontaneous, right? And that gives us the inequality, right? But we had to know whether the inequality was positive or negative. We've figured out that it's negative, right? Anyway. All right. So what I want to do for the last part of the class is as I mentioned, I want to kind of do a cookbook. Come on, let me resize this. Thank you. I want to do kind of a cookbook treatment of how you would solve second law problems. And this is from Levine. So let me write this down. Second law cookbook. So if you found a copy of Levine as kind of a second source, you can find this section. This is section 3.4 in Levine. But let me run through it, because the hard part about all this is when you're asked a problem, calculate delta U, Q, W, and delta S for this process. And it gives you a set of conditions: adiabatic, isothermal, blah, 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 blah. What is everything? And it's hard to keep everything straight. So let's try to do that, right? What if we have a cyclic process? A cyclic process, since S is a state function, delta S equals 0. In other words, dq over t equals 0. This is the way we've framed it so far, right? All right. What if we have a reversible adiabatic process? Now, reversible means that the Clausius inequality becomes an equality, right? So that's very important to realize. But the net result here is dq rev is 0. Adiabatic means no q, right? No q transfer. This is different from the first case. The first case, because S is a state function, any cyclic process is 0. So it doesn't matter what is inside the S, right? We return to the original state, delta S is 0. In case 2, it's adiabatic. It's not necessarily cyclic, but because it's adiabatic, the dq part of S is 0, thus the whole thing is 0. Okay. A reversible phase change. If you recall, a phase change is truly the only time we can experimentally get close to a reversible process. For all intents and purposes, an experimental observation of a phase change is a reversible process, right? So what do we have here? We have this. This happens at constant temperature, right? So we can pull the T out. phase change happens at a constant temperature. So we can pull the T out, 1 to 2, dq rev. Okay. Well, why is this important? This is important because if we are at constant pressure, Q rev equals QP equals delta H, right? So what we can say is delta S is delta H over T at a phase change. And you've seen this before, right? But we come at this the other way after we define free energy, which we haven't even gotten close to yet, right? We haven't even really gotten close to free energy yet. So let's think about this though, because we can make a further connection here. Delta H is greater than 0 for a phase change if it's melting or vaporization. Of course, it's the opposite if we go the opposite direction. So delta S is also greater than 0 for these processes. You can make the opposite connection or tell something about entropy going the opposite direction in the same way, but this is an example. Right. All right, so what if we have a reversible isothermal process? Well, this is really the same as a phase transition. In other words, a phase transition is one example of a reversible isothermal process, but it's not the only one. It's not the only one, right? So we end up being a little bit limited, but the end result for the S is the same. The only difference is for a phase change, we actually can measure the heat input pretty easily, right? We can use some sort of electric heater, right? We can take a block of ice, we can calculate the amount of energy, electric energy in joules that it took to melt that ice cube. We can equate that exactly to the delta H, and that gives us the S. There might be some other reversible process, expansion of a gas, or we could think of some sort of reversible expansion of a gas. We could measure that heat, and that will also give us the delta S. So in other words, these reversible isothermal processes allow us to calculate the delta S exactly, but it's about the only time we can do that. 3 and 4 are kind of the same end result, but different actualities. All right, 5. What if we do constant pressure heating, no phase change? In this case, the heat we measure is just the heat capacity, right? So let's look at this first. What if the heating is reversible, right? What we can say then is dq rev equals dq at, say, constant pressure, right, is Cp dt. Okay, so then what we have is we have delta S is the integral of 1 to 2 dq rev over t, but this is just 1 to 2 Cp over t dt. okay? If Cp is constant, this may be true for small temperature increments. Remember last time I drew kind of what the heat capacity curve looks like. It's kind of curvy, but there are certain areas where you could say, it's kind of straight. Then you could say this. Okay. Okay. What if it's irreversible? Well, it turns out that we can really, in practice, still do the same thing because delta S is a state function. So all it depends upon is the initial and final states, right? And it turns out that we can use the reversible definition for irreversible processes too. This is very powerful, right? So what I'm saying here is that if we have a state A and a state B, and our real process goes like this, then we can define a reversible path. I probably should have drawn those the other way, right? Let me do that. Because I think probably a squiggly line feels more irreversible than a nice smooth line. We can always define delta S. I mean, delta S is independent of path. So what this means is that if we can imagine a reversible process ending up at the same place from the same starting point, then the value is going to be the same. So we can always do substitution. We can substitute imagined reversible path. Right? This is pretty powerful. Okay. You may want to know how many of these do I have. I think there's 11 of them. No, there's 10 of them. So we're more than halfway there. We're more than halfway there. Or no, we're exactly halfway there because we've done 5 of them, right? So here's 6. 6. Reversible change of state. Of a perfect or ideal gas. Now, in thermodynamics, one of the things you notice is we start talking about a perfect gas versus an ideal gas. And it turns out they're not exactly the same. An ideal gas is not exactly the same. But I think for most people, it's a technical difference. It's a distinction without a difference most of the time, right? The way I think about it is a perfect gas is something you never ever see. It is the perfect definition of an ideal gas. An ideal gas is a gas that you're treating perfectly. So like I said, this is a distinction maybe without a difference. Anyway, well, now this is not to be confused with a phase transition. We're just changing the state. In other words, we're changing the thermodynamic state, not the physical state. Okay, well, what do we have here? dq rev, right, is going to be, if we rearrange the first law, then we get this. And remember, du is just cv dt. That's a very convenient thing to remember. Plus pdv, because it's minus dw, right, equals cv dt plus nRT over v dv, right? We've seen this before. We're just going through it again. ds dq reversible over t. Now, do you remember we did this, right? We remember in the when we used Clausius, we did this, but now we have dq rev over t defined as ds. So the end result is, right, if I just skip, I'm skipping a couple steps here, but we just did this a few minutes ago, really. Okay, so we get a heat capacity term and a gas expansion term, right? Now you can start thinking about this in your head, and you've heard about entropy before. You've talked about entropy before in earlier lives and other classes. Here, what we have in entropy is we have kind of a heat term, right? Which is kind of like imparting motion onto our particles, but we also have an expansion part, right? So we have kind of an internal entropy and an external entropy term. And then maybe that's the way you can think about these two terms. The other thing you have to think about here, right? And we did this a second ago in one of the other cases, is the heat capacity a function of temperature or constant? So you have to think about that. If you're doing a small temperature change, then maybe you can just pull out that heat capacity as a value, 4.184, right? The heat capacity of water, we're doing a small temperature change. But if it's over a larger region, then what you want to do is you want to substitute in something that's going to look like a virial or some expansion, right? This is what we did on the first problem set effectively, even though I didn't really announce what it was. What if it's an irreversible? I have to look at my computer for the time because my iPad is lying to me. All right, again, what we're going to do, we want to think of some reversible steps that will have us do the same thing. Maybe a series of reversible steps. Right? So let me give you an example. What if we go from P1, V1, T1 here to P2, V2, T2? So we're changing three things at once. Well, we might do this. We might go to P2, V2, T1, right? And then we might do this, right? So this might be, this first thing might be isothermal. And the second one might be adiabatic. Right? So if we can think about a two-step process, which is the same end result for our one-step process, and we can break those up, then that's what we're going to want to do. I'm putting this next one in for completeness because Levine mentions it. If you happen to go and look at Levine and look at this one, you might be a little confused. We need to know, for this particular process, we need to know how entropy changes with pressure, right? We do this later. But you don't have to worry about this. You're not going to be asked about any process that is going to depend upon the pressure. What about an irreversible phase change? Well, what's an irreversible phase change? Well, this is something like taking some liquid water at minus 10 degrees C and turning into ice. This is irreversible, right? This is like putting some water in a freezer, right? This is an irreversible process. It's not an equilibrium phase transition, right? So what do we do here? Well, you want to use a reversible path. And this is something you might not recognize, but we've done this already in freshman chemistry. At least it's in our freshman curriculum, right? So what you do is you take some liquid water at minus 10 degrees, 1 atmosphere, right? We take this to liquid water at 0 degrees C, 1 atmosphere. We take this to ice at 0 degrees, 1 atmosphere. And then we take this back to ice, not ices, ice, at minus 10 degrees C, 1 atmosphere, right? So here is what we're trying to measure, right? And we're going to do this in a series of reversible paths that we can measure, right? And since the closed loop is 0, we could say delta S equals delta S1 plus delta S2 plus delta S3, right? So we're taking advantage of the fact that delta is a state function. And we do this in thermochemistry all the time without really thinking about it as ramifications, because we're already just saying entropy is a state function. But we know how to do this. It's actually one of the first things we learn how to do. We just don't think about what it is. So now let's think about two perfect gases, A and B. And we have them in equal volumes, right? Separated by a wall that we can pull out. What happens if we pull out the wall? We know that they mix. We know this is spontaneous, right? We know that it's also not undoable. In other words, the gases are not going to spontaneously find their way back to each side, right? So the diagram is, and I should have this diagram. we have something like this. A, B, B, B. And we're gonna go B, 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 A, A, right? This is spontaneous and it's not undoable, it's irreversible. Now, this is something we haven't talked about in detail yet, but we will. But let's put down the result, because this is a very common result. And it is kind of intuitive. And it has to do, so right now what we're going to do is explain it, because I'm almost out of time. We're going to explain it in what we call positional entropy. Positional entropy basically relates entropy to the accessible volume, right? So if you have a gas, 1 mole of gas in a liter, and you have 1 mole of the same gas in 2 liters, then the mole of gas in the 2 liters has twice the entropy, right? So in other words, if you just took the first gas and doubled its volume, the entropy change is going to be measurable. It's going to be proportional to the volume. So what you start off with is that the entropy change is going to be proportional to the volume change. And it turns out that the entropy change for gas A is going to be the number of moles of gas A times R log of the volume change. And so what I'm saying here is V is VA plus VB. And here we have VA and VB. And delta SB is the number of moles of B times R log V over VB. This is also something we do freshman year, so I'm just kind of taking advantage of that. And because of the properties of logs, even if each initial volume is half of the total, the entropy change is not zero. The entropy change is not zero because of the way logarithms work, right? And what we're going to do is we're going to, in order to really understand this, is we're going to use the Boltzmann description of the second law, which is a state-based description of the second law. But we're not going to do that yet, basically because DeVoe does it a little bit later, okay? So it turns out that really the things the things that are going to be most common and useful to us, of course, don't really include 8, right? And for the most part right now, we're not going to worry about 10 because we haven't fully described it. But for all of the other ones, we have a way to deal with these. And so you can kind of look at this cookbook if you get problems like this and decide what to do. So it's always kind of a matter of knowing where to start and how to break up the problem into digestible chunks. And sometimes it starts with a digestible chunk. If it's a phase, if it's a phase change for water or whatever, then you can calculate the entropy change directly from the heat or the enthalpy. But if it's a more complex process, you might have to bite this into chunks, right? You might have to basically do a change, a slope as a run and a rise, right? Break it up into 2 pieces. You can take advantage of the fact that if you have a state function, all that matters is the beginning and the initial state, and however you travel between those 2 states doesn't matter. So it's actually kind of a powerful thing. Okay, so I went a little bit over. I'm really sorry if you have an 11 o'clock class that you have a little bit less time to prepare. Does anybody have any questions? I think problem set 2 looking at it, at least to me, feels a little bit not as bad as problem set one. Problem set one was a little disorganized too. But if you have any questions on that, just let me know. I'll be around today and, you know, even on the weekend if you need help. And
So for the exam,
mhm.
so you're just gonna open it Monday morning and we have to just turn it in by midnight?
Yeah.
Okay.
Yeah. And it's just, I'm just going to give you a PDF, right? And so you can answer it on the sheet. It's going to look like a regular exam, right? So I'm going to give you spaces to do your work. So if you want to, you can just work on it there. If you want to do it on a separate sheet, that's fine too. Just turn back the sheet, you know, whatever sheet you do it on as a PDF. That'll be fine. So what I'm going to do today is I'm going to finish that key and post that so you can examine that, and then I'll do the grading for problem set one, so you'll know about that too. Okay, I did post a quick video, quick meaning less than an hour, right? A quick video on solving the plotting problem. So I ran through all that because there were some weird details, and when I did it, it took me a long time because Qt Grace kept crashing. I will tell you that for me on my my MacBook Pro, whenever Qt Grace seems to crash a lot, it really helps to reboot my computer because it doesn't seem like it should have anything to do with that. But I noticed that the errors that the core dump, basically the description of why it crashed, anyway, it just led me to believe maybe a reboot would help. And so I actually had Qt Grace crash on me in the exact same place like 8 times in a row. And you would think after 2 times I would stop doing it and figure something out, but of course I kept trying it and trying it. And then I rebooted the computer and it was good from then on. So I don't know. It doesn't seem to me like that should make any difference if the program was well behaved, but I just think the program is not always well behaved. So you can try that. The other thing that I noticed, and I think I spoke to most of the people who are having this problem, and at this point you should have tried to use Grace and knows this problem. When you download that program and it's on a disk image, you have to drag that disk image. I'm sorry, you have to drag the application from the disk image to your hard drive because it will not run properly from the disk image. And that's kind of a pretty common thing for a lot of Unix type programs. Okay. Okay. I hope you have a good Friday, and let me know if you need any help with any of these problems. I'll be around.
What time will the exam be available on Monday?
The exam will be available no later than 6 a.m.
Okay, thank you.
It could be available as early as midnight.
Okay.
Right. But definitely by 6 a.m. Okay.
Thank you.
Okay. I'll see y'all later.